Okay, the recording has started. Can everyone see the camera on your full screen? Can everyone see the display on the full screen?
Right now I'm seeing the view of you, the camera that's behind you.
I'm sorry.
Right now I'm seeing full screen, the camera that's behind you.
Yeah. Right. You should be seeing that camera. That's I should
Yep,
be looking
that's
at.
correct.
So okay. All right, so you can see this view. So all right, welcome everyone to the in-lab portion of CS101, conducted susceptibility on power leads from 30 hertz to 150 kilohertz. I'm planning on doing all stuff in the lab. That's why we're here. So all demonstration measurements. So I have the charts from Monday up in case a question arises where I might want to refer to them. But if absent that, I'm not planning to show any charts. This is all, just the practical application. And so forth. So definitely encourage you to go watch the video if you weren't able to participate in Monday's session. Of course, this is being recorded as well for posterity. So so basically just picking up where we left off on Monday, we're going to plunge into the CS101 test method, and I'm going to show you basically how it works. So I'm going to pick up the camera and walk you around the room here and show you the setup. It's the same basic unit under test that I've been using for these demonstrations. We'll get to that shortly. We're not immediately going to be testing this, but we will work up to it. This is the power converter that we use for our conducted emissions tests, and so it'll be the same basic test article. So it's bringing 30 volts in, or 28 volts in, giving you plus and minus 15 out, and then we go out to a pair of load resistors out here. Power converters don't like to be open circuited. And we have our power source and capacitor network over here. So just any workhorse lab supply. It's turned off now because we're not powering up the unit under test. But we're going through our capacitor network here, a pair of 10 microfarad feed-through capacitors, and our 10,000 microfarad line-to-line. Okay, so it's just part of the same setup we've been using. So now for the CS101 setup, the heart of it is the injection transformer. I'll go around to the front and show you the model number. It's basically the standard injection transformer used for CS101 and CS01 before it. Eventually, we're going to hook it up in line with our power feed with the red wire coming off our capacitor network. It's disconnected now because we're going to pre-calibrate first. We'll come back around here in a moment. But so the center point of the whole setup is this injection transformer. So it's the Solar Electronics 6220-1A. That's our workhorse transformer we use for pretty much all CS101 testing here at Goddard. There's a slightly different model number. I forget if it's the -2 or if it's the 1B that takes more power. But this takes 100 watts. So this already this can handle basically the power that you're going to use for most applications, and just the other unit looks pretty much the same. It's just a little beefier for more current and more power. But it's a 2-to-1 step down. See it right there. The 2-to-1 step down transformer works from 30 hertz to 250 kilohertz. We generally just use it up to 150. Hey, okay. And so you need to drive it with a signal. So we have a signal generator. Specific model isn't really all that important, but it's a Keysight 33600. Apologize for the brightness. Kind of hard to see that. So once we get going, I'm just going to show you the scope. So you won't be seeing this, but I'll just be adjusting frequency and amplitude. And then we have the signal going through a drive amplifier, and this thing is very noisy. I don't know how much microphone's picking it up, but this thing is pretty noisy, so I'm gonna do my best to talk loud over it.
What's the source, John?
Hey,
What's
John.
the source? What's the
What's
source
that?
impedance? I'm sorry. What's the source impedance on the amplifier? Do you know?
Well, that's going to be central to the discussion. It's actually shown down here. Output impedance of 2 ohms,
Okay.
at least as advertised. That's likely that probably does vary over frequency, and that's one of the things I'm going to show you. So,
Hey, John. One go
Yeah.
back. Hope this is done. You said 100 watts on the transformer.
yeah.
What does that mean? Is that the DC power capability?
That's a very good question. I would take that to be like the I squared R drop across it, but I don't know if that's actually what that means.
All right.
I'll have to look
No
that up in the
worries.
spec sheet. But
No worries. Thanks.
yeah, I think does it actually specify? It does say secondary current 50 amps DC. So you can put up to 50 amps of DC current through this thing. Because I mean I mean we're putting it in series with a DC power feed. So it has to be able to handle a pretty substantial amount of DC current, and then you're putting an AC current ripple on top of that. So
Yeah,
in any event, the first thing we're going to do is pre-calibrate into our half ohm load. So let me go back around here and show you that. So we have our half ohm load, and it's a BP power resistor. I don't recall how much power this thing takes, but it might be 250 watts. So this is a pretty, I mean, you want to use a BP power resistor when you're doing this, not one of those quarter-watt carbon resistors. So we're taking the secondary of the transformer and just going across this half ohm load, and then got a differential scope probe, a differential voltage probe, just going across the resistor, and we're also going to look at the current going into it. Now, the traditional pre-calibration step really is just establishing what signal generator level you need to get the desired power or voltage across the load resistor. But I'm monitoring the current as well, well, just to make a point. So we'll get to that. So any questions on the basic setup? And we'll actually get to taking some measurements. Okay. Now we'll set this thing back on the tripod. Move it up so you can see the scope. Now, I had to make a judgment call on scope settings. I prefer the dark screen with the bright traces, but when I do that, the numbers over here that I'm going to read off are completely illegible. So inverted the scope screen so that you have the more bland display of the traces, which I hope you can still see, but you should actually be able to read the numbers off of here so that you're not just believing me when I tell you what those numbers are. So can everybody see the scope all right?
Yes.
Yeah, the trace is very clear.
The other unfortunate thing is with this display, you're getting that flickering action, but I hope it's not too distracting. Here, I'll even show you the default setup, like what most people are used to seeing is this. And that's what I'd prefer to show you, but the brightness over here, you just can't even, at least on my screen, you can't even read those numbers. So bear with me, we'll get through this. So, but I'll go ahead to the other display so you can actually see what the numbers are. And And if you start getting too dizzy from that flickering, let me know and we'll go back to the other setting. Okay, so what I haven't shown in this setup, because I mean I'm not using it in this setup, usually you will have well, most labs will have some sort of control loop where they'll have the signal generator and the scope connected to a computer. In our case, it's a laptop, so that the setup is portable, running whatever control software you're using. We use Tile, and so when you have an automated setup, you can do the test a lot more quickly. Now, I'm not intending to show any of the specifics of any particular software application. I want to show this, just the particulars of how this test method works. So we're going to do this manually. I don't have the laptop hooked up, and I don't know how to run Tile all by myself. But that's not the point. We're going to run through this manually and do just a representative sampling of frequencies across the range, 6 to be exact, instead of several hundred that it would be in the normal case. And but just to show you the general mechanics of how this test method works. So we're starting at 30 hertz, and because I'm old school, and since we're doing this manually, I'm going to write down numbers in my notebook, and I'm going to use a fancy old device that I call my personal effective note taker, or PEN. So try it at home. They still work very nicely. So we're starting at 30 hertz. That's what you're seeing. And the top trace is the voltage across the resistor, and the bottom trace is the current. So the main thing that we're doing is we want to get, I'm going with the GEV's default voltage limit of 1 volt RMS. So over here, the measurements that I've set up are AC RMS. Because we're just injecting into a resistor, there's no DC component. There certainly shouldn't be. So whether you just use RMS or AC RMS shouldn't matter. But once we're actually injecting on top of the DC power feed, you only want the AC component. Okay, so if your scope has that capability of giving you an AC RMS measurement, that's what you want to use. Because if you just do RMS, then it's probably, at least some of the scopes that we've used, will give you that 28 volt component as part of the measurement, and that doesn't help you. It'll tell you that you've got 28 volts RMS, and that's not what you're interested in. You only want the AC component. So this AC RMS is important once we're actually injecting into the unit under test, which we're working up to. Okay. But the entire point of the pre-calibration exercise is to record the signal generator setting for what it takes to get your desired limit, in this case, the default 1 volt RMS, across your calibration resistance. Okay, everybody clear on that?
Yes, sir.
Okay. And I'm going to record the current too. And current's kind of extra credit. The main thing is if you're doing the pre-calibration step per tradition, as defined, decades ago, it was really only about voltage, because it just wasn't really standard practice to monitor the current directly in real time. But now we have that capability, and that's one of the points I'll be making here. So I'm gonna just record the signal generator setting, and then for what it takes to get the 1 volt RMS, and then I'm also going to record the current. And I'm not going to perturb the camera at this point, but the signal generator here is down below, and we generally do things in terms of dBm. So that's what I'm going to do. Actually, there's one other thing I'm going to show you here. On the amplifier, the lab guys have put a little sticky next to the gain knob here. This is the max setting for a 0 dBm input. So that's where I set the gain. I mean, you can set the gain to wherever you want it. Once you set it, it's pretty arbitrary, but once you set it, you leave it alone for the duration of your test. So I'm just setting it to to that line. That's the default setting that we tend to use. So there we go. So that's that for a 0 dBm input. That's the max setting you want to use. And as we'll see, we're actually going to be less than 0 dBm coming out of the signal generator. So I'll just show you the signal generator real quick. And again, the screen is very bright, but the frequency is on the top. We're 30 hertz right now, and then it's at minus 9.6 dBm right now. So these signal generator settings are going to go into a lookup table. In this case, just in my notebook. But with an automated setup, when you run your pre-calibration, they'll go into some file, probably a CSV file or some equivalent. It'll be a lookup table that establishes the not to exceed level when you are injecting into the unit under test. So this level will be the level you do not exceed. If you're not able to establish the 1 volt RMS or whatever your limit is, but you get to this pre-calibrated level first, you stop. And as I said on Monday, you still meet the requirement. There's no waiver necessary for saying we weren't able to get the voltage, we had to stop at the pre-calibrated level. No, you've met the requirement. You've met the full intent of the requirement. Because you don't want to keep trying to crank up to 1 volt RMS when you've got a low impedance and start putting a lot more current into your unit under test than you want. Okay, so with all that, let's get cranking. Because electronics tend to drift with temperature a little bit, I had this set to give, every time I put my hand in there, it seems to change the focus. So I'm going to try not to do that. But you can see measurement 1, AC RMS, that's the voltage. Measurement 2 is the current. Measurement 3 is the voltage probe that's hooked up to the converter output, which we're not using right now. So you can ignore measurement 3, but I just have that set up so that we can get right to that when we get to that step. So I had it set so that the AC RMS was right around 1 volt, but it's drifted up to about 1.18. So I'm going to take this down to minus 9.7 dBm. That's what when I did this yesterday, that's about what I got. So minus 9.7 dBm at 30 hertz to give. I'm going to go ahead and write down all the significant figures. 4 significant figures is overkill, but I'll write them down anyway. The first decimal place is probably all we need. But so okay, the 1.008 volts AC RMS. The current is 1.996. Okay, so if it's 1 volt across half an ohm, we would expect 2 amps. That's essentially what we're getting, just shy of that, but about 2 amps. So that's what we would expect. Okay, and that's pretty much it for that frequency step. Now I'm going to deliberately do something bad to make a point here. Now we're only, I don't know about bad, but basically something you're not supposed to do. I did this accidentally the other day, and I thought this would be good to make a point. I'm going to just jump to 100 hertz, okay, without changing the signal level. So we're at 30 hertz now. I'm going to just jump to 100 hertz. Well, see what happened there? The voltage about doubles, and it's actually flipping. So I got to, there we go. I got to change the scale so we can actually read it. So it went up to about 1.8 volts. So the point there is that whether you're doing this by hand or especially if you're doing it in a control loop, you want to drop the level before you jump to the next frequency. Okay, and you can set it to minus 6 dB, minus 12 dB. Minus 12 dB is generally enough. And also, in the real test, you're not going to jump from 30 hertz to 100 hertz. The frequency steps down at the low end are 5%, 0.05 F naught. So after 30 hertz, your next frequency step would be 1.05 times 30 or 31.5 hertz. I'm not going to step through all those by hand because it would take you a very long time. But so I'm going to go back to 30 hertz. And oh, and you can also see the waveform is looks a little weird. Right? It's not a completely clean sinusoid. So if you're just reading this, sometimes people will read the voltage just into an RF power meter or something like that, or even maybe an AC voltage reading off of a DMM or something like that. I definitely recommend you actually look at it on a scope because you'll miss things. You know, the scope will tell you is the waveform distorted. It may not really change how you run the test, but it just gives you more visibility as to what the signal looks like. As we go up in frequency, I mean, you're really pushing the transformer pretty hard at 30 hertz. Even once we get up to 100 hertz, it's a bit cleaner. So anyway, so I'm going to go to the amplitude. I'm going to drop it by, it's a pretty good jump from 30 to 100 hertz. I'm going to drop it by about 10 dB. And so now we'll go up to 100 hertz. Okay. Now we can bring it up to level until we're seeing our desired 1 volt. Change the frequency scale. Okay. There we go. Go down a couple tenths of a dB. Nope. More. Okay. So we're at 1 point, and you see the sinusoid's a little cleaner now. So one other thing I'll point out, the voltage waveform has a fair amount of fuzz riding on top of it, and the current waveform is cleaner. So I'm triggering on the current waveform. When I trigger on the voltage waveform, it's a little less stable. So you can see the trigger is right there on the current triggers. So all right, so write down our signal generator setting is minus 15.6. Voltage is 1.0015 now. And our current is 1.990. So it's still close to 2 amps, but it's coming down. So, you know, it's a little bit less efficient, whether there's, you know, inductance is starting to creep in and things like that. But anyway, that's 100 hertz. So I'm going to drop by about 6 dB and go up to a kilohertz. So I'm just going to do power to 10 at this point. Okay. Change the frequency scale or time base. Now I'll bring up the amplitude. A little too much. Pretty good right there. All right. And just because of my own, whatever you want to call it, OCD or anal compulsive tendencies, I always would rather be just a little bit above the desired reading. Like you might say 997 millivolts is just fine, but I'd rather be above. So, and that's another setting in your control loop where you can set the tolerance. And we usually go with minus 0 dB and plus however much, plus 1 dB or something like that. You want to at least get the desired reading and you know, whatever slop on top of that. And that's something you got to play around with in your own software, because the tighter you make it, sure, the tighter tolerance you have around the desired limit, but the longer it's going to take to actually level on it. So that's just something you have to play with in your own software loop. So anyway, this is, yeah, I had about minus 16.6 before, and now we're at minus 6, you know, at minus 16.6 again. So pretty minus 16.7 BDM, if you can't see. But our voltage again is 1.005. And our current is, well, it's right around, that's right at 2 amps. So that's good. We're still kind of hanging around V equals IR, still kind of holding here. So, all right, now I'm going to go up to 10 kilohertz. And I know the signal generator setting. All right, I'll maintain good practice here. I'll drop by about 6 dB. Go up to 10 kilohertz. All right, and bring the level up. And get on a couple temps. It was about minus 16.2 before. There we go. Minus 16.2. dBm is what gives us basically 1.0, I'll call it 1.002. And the current is still right around minus, I'm sorry, 1.989 amps RMS. Okay. And I'll drop the amplitude about 6 dB again. And now we'll go up to 100 kilohertz. All right. Now level is dropped. Now the transformer is starting to get a little bit less efficient. We're starting to push it pretty hard again, getting up to 150 kilohertz. So we need a little more signal level to get our 1 volt. There we go. Okay, so we're at about minus 8.8, right around what we had before. Yeah, minus 8.9. So about minus 8.8 dBm, giving us 1.0, let's call it 1.010 volts, close enough for government work. And now we're about minus one, or I keep saying minus, sorry, 1.748 amps. Okay, so we're coming down a little bit from the 2 amps. So this the inductance of the wiring, getting to the resistor, things like that are starting to limit the current a little bit. But we're still, I mean, we're by design, by goal, we're getting our 1 volt RMS across the resistor. Okay. All right, one last data point at 150 kilohertz, and we'll drop our amplitude up to 150 kilohertz. And then our amplitude up. All right. Okay, yeah, it was about minus 3.1 before, so this is minus 2.8, a little bit higher. But minus 2.8 dBm to get 1.002 volts, excuse me. Now we're about 1.551 amps RMS. Okay, so that's our pre-calibration.
Hey, John.
Oh, so one of the points I was going to make is when you hook this up to your control loop, the driver that you have in your software needs to read these values off of your scope. And so you need to have a driver that's matched up to the scope you're using. And I think for a while, the driver for a specific scope we were using would only work when it only worked like on a straight up RMS value, which forced us into AC coupling the signal that we were looking at, which I mentioned on Monday, and we'll get to that when we hook up the unit under test. I really don't like doing that. If that's how your software works, and it's only going, it only gives you the option to read a straight up RMS value from your scope. Well, then that's what you have to do, but you have to be extra careful because you could miss. AC coupling can fool you, and I'll get to that here when we hook up to the unit under test. But anybody have any questions about pre-calibration step before I move on to the next step?
One question in case you don't cover it. So if you were gonna do this test manually like you're doing, you would still drop amplitude between frequencies. In other words, you don't go to the level setting that you noted in the pre-cal right away. Is that right?
Yeah, I mean yes, when you go to inject in the unit under test, the input impedance is going to vary as a function of frequency. So you don't know what the input impedance is going to be at the next step. So it's always a good practice to drop the level before you go up to the next frequency.
Understood. Thanks.
Yeah. Yep. Okay. All right. So the next step is not something that a lot of people do, but I think I would recommend it be kind of standard practice. I was at a test at a contractor facility and last summer, and they did this verification step where they played back those levels into a short circuit. So, would you mind operating the camera? Sure. Well, hope you don't all get dizzy. Okay. One little safety thing we will do. I'm going to turn off the signal. So let's see here. Output off. All right. And so the scope is showing flat lines. So don't really want, I'm going to keep the amplifier on. That's okay. Because the amplifier, you can see that it drifts over time. It's once you have it on, it's best to just leave it on. But there's no signal flowing through it, so we're okay. So the next thing I'm going to do is disconnect our voltage probes. We're only going to look at current in this next step. I don't need the voltage probe, but I'll need it for the step after this. So I'm going to just disconnect the negative lead. And I'm just going to put our positive lead across the transformer. Okay. All right. And you can close up on that. Like the arrow on the current probe is going, in the direction of positive current flow. Doesn't really matter for what we're doing here. But when you're looking at the conduit, it's good to pay attention to what direction you care about. So when we actually are looking at the relationship between voltage and current to look at impedance into the unit under test, that will be important. So it's just good to always pay attention to the direction of current flow, that it's in the direction that you're interested in. Okay. But for this step, we're just looking at magnitude. So if you're really going to do this properly, I would put a very short wire between these two terminals. But in the interest of time for the demonstration, this is fine. So I'm just because it's very convenient to just move the wire like I just did. So we're just deliberately shorting out the transformer secondary, and we're going to measure the current, and we're going to play back those pre-calibrated power levels. Okay. So yeah, I'm going to put it back on there. The slot right there. Here. Okay. Now, since we're only interested in current, I'm going to get rid of the voltage trace. And so I'm just going to look at my lookup table, and we'll go back to 30 hertz. And start with a low amplitude. For playing these levels back, it's going into a resistor. You're not going to harm that half ohm resistor, but it's still just good practice to lower the levels between frequencies. So, I'm sorry, it's 3 kilohertz. 30 hertz. All right, we'll turn the signal back on. We're gonna have to adjust the time base. And it's pretty good amount of current, and we are clipping, so. All right, so we can ignore the top waveform. We're only, or the, I'm sorry, the top measurement. We're only looking at measurement 2 here, ACRMS. So, the 30 hertz playing back are, oh, sorry, I hadn't adjusted the signal level. So we were at minus 9.7. All right, so now at 30 hertz, minus 9.7 dBm, we are getting just over 4 amps. All right, 4.074 amps. All right, so if we just call that 4 amps, that's what we would expect if for our advertised 2 ohm source impedance of our drive amplifier going through our 2-to-1 step down transformer, it's going to step it down to half an ohm. So you have half ohm source impedance going into a half ohm load. So to get 1 volt across half an ohm, you would need 2 volts at the upstream side of your source impedance. So the short circuit current is going to be determined by that open circuit voltage divided by the source impedance. Okay, so if this tells us that our source impedance is looking like pretty much right, very close to half an ohm at 30 hertz. That's good. That's what we expect. Okay. And this means that if you do this pre-cal without monitoring the current in real time going into the EUT, your short circuit current limit at 30 hertz will be 4 amps. Okay. Now we go to 100 hertz. I'll reduce the amplitude first. So our amplitude at 100 hertz was minus 15.6 dBm. We'll go to 100 hertz. Okay. Now our current is 2.748, call it 2.8 amps. 2.7, right? We go shy 2.75. So we're not quite getting 4 amps. So that means that our source impedance is probably a little bit higher. Right? It just means our source impedance isn't exactly half an ohm. But our short circuit current, at least with, well, and that wire is adding some inductance. Right? That's why I said if you really wanted to do this properly, you place a very short piece of wire between those terminals and clamp your current probe around it. And we'd probably be getting a little bit more current here, but this is sufficient to illustrate the point. So now let's go to a kilohertz. Our level was minus 16.7. Okay, now our current's about 2.522 amps. So the current's going down a little bit. Now that's not such a bad thing if your short circuit current isn't quite at 4 amps. It may mean you're getting a little bit of an undertest. If you're going into a low impedance, you're not going to get quite as much current as you might think you would. But at least it's, keeping your hardware safer. So all right, now so at 10 kilohertz, our level is minus 16.2. Kilohertz. Okay, now it's 2.502 amps. So pretty close to what we had there at a kilohertz. At 100 kilohertz, our level was minus 8.8. But this clearly is a little tedious to do by hand, but again, to illustrate the point, when you automate it, it will go much faster. Okay, so at 100 kilohertz at the pre-calibrated setting, we're just over 2 amps. We'll call that 2.097 amps. Right, and then the last data point at 150 kilohertz. Oops. We're at that's 2.8. Okay. And that's about 1.92. Yeah. Okay, so at 30 hertz, we got our full 4 amps, just playing back these pre-calibrated levels. But the current goes down as we go up in frequency, which any number of factors could contribute to that. But it means that the impedances aren't quite what you think they are, or aren't quite ideal. So the resistor itself may have some inductance that starts kicking in. The wiring, just the loop of wire to get us from the transformer to the resistor is going to have some inductance that may start affecting things. At 100 hertz, I wouldn't expect that to be real significant, but above about 10 kilohertz, probably. I mean, about 10 kilohertz is where some inductive effects can start kicking in. So just when you're relying only on the pre-calibration step, the maximum current that you can get may not be quite what you think it is. Okay, so that's why, well, it's one of the reasons I just recommend monitoring the current directly when you're injecting into the unit under test, even if you do the pre-calibration step. So any questions on this before we hook up to the unit under test for the main event? Okay. One thing I'll point out here, I don't really recommend that you look at. So we're going to do the thing I'm about to not recommend, but hey, but I don't recommend looking at least using the display on any of your like drive equipment as like a be all and end all. But it's an interesting data point. What this is telling you is that it's putting 5.6 volts RMS out. Okay, so we pre-calibrated to get 1 volt RMS across our half ohm load, but it referred to the transformer secondary. There's was a half ohm source impedance when we did that. So our open circuit potential should have been about 2 volts RMS. So this is telling you that due to any number of factors, probably transformer inefficiencies, among others, we're having to drive the amplifier a bit harder. And instead of getting 2 volts RMS out, we have to drive the amplifier to 5.6 volts RMS to get the desired pre-calibrated voltage across the resistor. So just an interesting data point. Again, we're not using this to level on, but it just gives you some indication that what's coming out of the amplifier is higher than what is needed to actually get the desired calibration voltage across the resistor. All right. If there are no questions, we will go ahead and hook up to the unit under test. Let me turn off our drive signal. And so remember that one of the big guidelines when doing CS101 is you want your drive amplifier to be turned on and stabilized before you turn on the power to the equipment under test. Because without your drive signal, well, it's turn on the drive amplifier, but also have your signal source connected to it. Yeah, please. Because you want the amplifier's output impedance mapped to the transformer secondary so that it looks like your half ohm resistive, mostly, ideally resistive connection mapped to the transformer secondary when you're turning on the EUT power. Because if not, you're just getting the full about 1 millihenry inductance of the secondary coil in series with the power feed, and that can and has been shown to cause some instabilities. Like you can get significant ringing during power up, and you can stress or damage the input stage of your EUT, and you don't want to do that. So
Yeah,
at this
John,
point,
want to echo
disconnect.
that.
Is there a question?
No, I just wanted to echo that exactly. That's very important to do, either to turn on the amplifier or to short the primary to make sure that you don't see that full inductance.
Yeah, sometimes, and I don't have it handy, but sometimes we do put a 2.4 ohm resistor on the primary for that reason. And I think sometimes when we left things set up overnight, like if you're doing some CS101 at the end of the day and then you're going to come back the next day, we'll sometimes put a 2.5. I think it's a 2.4 ohm resistor module that plugs right here into the transformer primary.
Yes.
But yeah, one way or another, you want to make sure you've got a controlled resistive impedance mapped to the transformer secondary when you're hooked up to an EUT power feed.
Yeah, that's right. So that your test crew, not the EMI, but the people that your own crew that brings the hardware, they're used to normally powering everything up for a checkout and stuff like that. They have to make sure with the transformer in that resistor is there or the amp is on.
Right. And it's incumbent upon everyone participating in the test. So certainly the EMI test engineers need to be clear that we're going to turn on our equipment before the experimenters turn on. But also the experimenters need to be aware of that so that they ask the question, we're about to power on, is your CS101 injection equipment fully powered on and ready? So it's just encouraging everyone. So even if you're not an EMI test engineer, just being aware of the test method sufficiently to ask that question, because it's everyone's responsibility to make sure we do this test safely. And I should have pointed this out on Monday, so I'll point it out now. My personal opinion, and I think this is shared by many, I think this is the most risky test that we do. Even CS114, the injection is a little bit less efficient, and when you're looking at radiated susceptibility RS103, you certainly can stress and damage hardware with radiated susceptibility, but the coupling is much less efficient, so that if you screw up and do an overtest with RS103, it takes a pretty significant screw up to get to radiated levels that could actually, could potentially harm flight hardware. Here, you're injecting your signal directly in line with the power feed to the unit. So if you screw that up, the threshold between the screw up and possibly damaging flight hardware is not very high. It's much easier to cause potential damage to flight hardware with this test if you're not paying attention to what you're doing. And so if that scares the hell out of you, good. It's kind of the point, but to make you aware of all the precautions that are needed to do the test safely. It's like driving a car, driving a car can be a very unsafe thing to do, but when you're paying attention and you're on your guard, you can do it safely. So anyway, let's go ahead and hook up to the test. Is there another question?
No, just echoing that exactly. I've said that to my team members in the past.
Excellent.
CS is the test that I'm most worried about.
Yeah, for all those reasons. Okay, let's go ahead and hook up to the EUT and one last look at the scope. Yes, the signal is off. And I thought about just using clip leads here, but no, we will actually do this properly and safely. It only takes a few seconds to do this. So, Okay, so here is the power feed from the capacitor network. So that's our positive lead. And so that goes to one terminal of the transformer. Again, polarity doesn't matter too much here, but you know, I mean, it's an AC signal that we're injecting, so and then so this wire is, you can see, is the feed that goes to the unit under test. So you're just putting the transformer in series with the power feed by design.
And John, while you're working here, this reminds me of another thing I do, and that is that with CS, I usually will do a safety mate at my hardware because you've broken out the power leads and the potential for swapping is there. So I always do a safety mate.
Yep, that's good practice. Okay. And, you know, having multiple eyes inspect the setup before you actually apply power is always a good idea. You know, so you're positively coming off the capacitor network and generally going all the way back to the power supply, right? Don't just trust that it's a red wire. We've been bitten by that before as well. So the red wire is going to this capacitor, going to the red wire that's going to the positive terminal of our power supply. Then the black wire from the power supply going to the other capacitor to the black wire. Oh, there you go. Okay. So it's always good practice to verify it all the way back to the power supply. But the red wire is going to the positive terminal of the power supply. Negative terminal is going to the black wire. And so that pair of wires going to the capacitor network. Black wire is marked side A return. That's from probably an earlier test when we were doing side A and side B, right? But important thing is return. And the red wire is going to positive, going to the red wire on the other side. Then the red wire is going to our transformer. And then the other terminal is going to the EUT, which is our power converter. Okay. All right. Now we move our probes over to the EUT. Let's get the chair out of the way. Hold on. Sorry, probably all getting dizzy here. Just moving the chair so we can get into the test setup. Okay, so one of the things we want to look at is the voltage across our input terminals of the EUT to our power feed. So we have this over here. There's this little doodad that we can hook up to these banana terminals that provides a handy thing to clip on with our voltage probe. So again, high impedance differential voltage probe is what you want here, so that you're not connecting the return lead of a standard scope probe is going to go to the scope chassis, which then ties to facility ground. In a lot of cases, you might be able to get away with that, but it's not a good habit to get into because that can affect your grounding, you know, especially at the low frequencies, right? You're starting at 30 hertz, and you're going to go right through 60 hertz, so it can affect. It can definitely cause some 60 hertz ground loops that could cause some weird things to happen in your setup. So I can't emphasize enough that you really want to use a differential voltage probe as much as possible. They're not real cheap, but they're worth every penny if you invest in them, right? And we have a second one here that's monitoring the voltage output. So let me get the current probe hooked up, and then we'll then we'll talk about that. So we're gonna move the current probe over to the input as well. So here again, in this case, I do want to pay attention to the direction of the current. So there's our arrow that's going to be going into the EUT input terminals. It's a pretty beefy wire. It's power, right? So the current probe is just big enough for it. So now we're looking at the voltage going into our 28 volt feed and the current. And as I said Monday, I highly recommend just monitoring, not only monitoring the current, but actually incorporating it into your controller. Because that's the best way to tell, are you getting into a high current condition? You're actually looking at the current and you set the current limit to the 4 amps. That corresponds to the 1 volt limit into the half ohm load. And the important thing there is, because I've had this discussion with people, isn't 1 volt into half an ohm 2 amps. Well, yes, it is, but it's the open circuit voltage of 2 volts that you need across the half ohm source impedance to get you the 1 volt into your half ohm load. So the 4 amps comes from 2 amps to 2 volts of open circuit potential across the half ohm source impedance. Okay. So, but the best way to actually verify that you're that you're not getting too much current into VUT is to monitor it directly and incorporate it into your controller. So a voltage limit for CS101 is an incomplete limit. You must have a current limit one way or another, whether it's a direct current limit that you intend to monitor in real time and be part of your control loop, or do the pre-calibration step. One way or another, you have to specify that, or it's an incomplete limit. Okay, so that establishes injecting the desired signal level. So we're going to be monitoring the voltage and the current. Now, as an equipment provider, you have to define what are your performance metrics? How do you establish whether you have a susceptibility or not? We get that question all the time. Well, how do I know if I'm susceptible? And if I wear a lot of hats, right? So sometimes I'm on the test side, sometimes I'm on the project side, sometimes I'm both. But if I'm more on the test side, if I'm more just supporting a test and I'm not as intimately familiar with the project or the box that's coming in to be tested, my answer is I have no idea. You know, you're the equipment provider. You are the one who knows what does it mean to say your box is working properly. So this is where discussions with the project as early as possible are essential to help them define, okay, here are the things that we're going to look at during these susceptibility tests to evaluate whether or not we have a problem. For a power converter, it's pretty straightforward. It's just the output level, right? So I've got another differential probe here across the plus 15 volt output, and we're just going to look at ripple on it. Now it's probably a bit more complex than that, but for this demonstration, I'm just going to be looking at the ripple of the plus 15 volt output on the scope. Okay, I see that there's a question in the chat. By the way, I'm not really looking at the chat, but I'll look at it right here. Oh, okay, that's Steve Glockner's question from a while ago, so we did address that. Okay. All right. Everybody good with what we got here? And we'll turn things on and start looking at what we got.
Yep, looks good, John.
Okay. Yes. Okay. We will turn our voltage back on. It's like some 60 hertz ripple getting through. And I'll turn on our output. And let's see here. Anything else I want to point out? Now we're going to start at, let me set the signal generator to start back up at 30 hertz. I think our input's is way down. Okay, so our amplifier is powered on, and I haven't turned it off. the amplifier is still powered on and operating and warmed up. So far so good. We inspected our signal connections, so we're ready to turn on the EUT power. Okay. One thing I'll point out on our the lowest trace here, that's our 15-volt output. A little bit hard to see here, but the line is sitting at 0 volts, though the reference here is sitting at plus 15. That's by design. That's one of the other points I'm going to make here is you're going to be looking at AC ripple on top of a DC level, both for voltage and current, and the output level here, the 15 plus 15 volt output. There's also a minus 15 volt out of the power converter as well, but they'll look pretty similar. And sake of discussion, I'm only going to look at one. But the tendency is to apply AC coupling to a signal like that so that you can expand around the AC component without expanding the DC component as well. And I understand the tendency to do that, but it's not very helpful. So let me turn on the power and then we'll talk about that. So watch all three of these, but in particular the top and the bottom traces when I turn the power on to the EUT. Okay. The bottom one is already set up the way I want it. But so all right, I'm gonna turn power on. 3, 2, 1, fire in the hole. All right, so what happened? The bottom trace went up to the reference line, because I already set that for the DC offset that I wanted. I wouldn't call that cheating. I'd call that advanced preparation, but call it what you will. The top trace went off the screen, right? Because it was centered around 0. For pre-cal, we were centered around 0, right? Just going across the resistor. But now we're riding on top of the 28 volts. So now we got to find our signal. And so again, I don't want to AC couple, and we're not going to do that. But so we collapse our scale. All right, now we're at 10 volts per division. So there's our signal. There's our DC level. So when you expand it and you want to try to get more resolution as to what's happening there, well, okay, you expand the vertical scale. Well, you lose the signal because it's expanding the DC component as well. But the more effective way to do that is to set an offset. So however your scope does it. So hold on. We dial it in. All right, so it's 28 volts ish. So we do this sort of iteratively, but we do that and we expand the vertical scale, and then we can fine tune the offset to center it up on the display. Not a big fan of touch screens, but they are. Okay. That's more or less centered. We'll want to do the same thing here on the current. The DC component of the current's not too bad, so we don't really have to muck with it too much, but we'll do a slight bit of mucking. Okay. And all right, the offset is actually okay on the bottom trace for the moment. And we want to tweak that a little bit. All right. Okay, so this is real injection into our power converter. So the top trace is our injected potential. And the middle trace is the current, and the bottom trace is the output voltage, is our plus 15 volt output of the converter. Now I don't even have the I don't even have the drive signal turned on. So I think that's just 60 hertz. In fact, it probably is. Actually, wait, it's 2 microseconds per division, so that's a little faster than 60 hertz. So that's just what the converter is doing. Right. That's right. At 400 kilohertz switching, the period of the switching is about 2.5 microseconds. So this is just the normal behavior of the converter without even the signal being applied. The transformer is in line, the amplifier is on, but the signal generator is disabled. The output is disabled. So this
Hey,
is
John,
just, yeah.
refresh my memory. The green line is the input current, the input ripple.
Yeah, the top trace is the voltage, the middle trace is the current, and then the red trace here at the bottom is the voltage output.
Okay, copy, thanks.
Okay. So now when we turn on the signal generator, it's going to superimpose our injected signal on top of this. Okay, so let's do that now. It's still at a pretty low level, so we're going to have to tweak that. So we'll turn on our injected level, and so we're injecting 30 hertz. So you can see it looks kind of weird with this horizontal display. So we actually need to get down to about, or in a millisecond. Yeah, so here we go. There's our injected signal now. You see, it's basically a triangle wave. Oh, hold on.
Yeah.
Turn the trace off. Didn't mean to do that. All right. So the voltage looks largely essentially like a triangle wave, and now I've still been triggering on the current. So let me the trigger is going to get kind of wonky here because there's a lot of noise on that on the voltage input. But there we are. So,
Some triggers have a high frequency reject.
yeah, there's a lot of high frequency stuff just from the power converter riding on top of this. I mean, it's the 400 kilohertz switching frequency and all the harmonics. So this also illustrates that when your control loop is just looking for one number for your AC, your AC RMS ripple, it's kind of incomplete, right? I mean, that's all your control loop is looking for, and that's all well and good, but just looking at the signal on a scope just at least tells you a bit more about what's happening. But it just so happens that what I set the signal generator to, the signal level is minus 13.8, but we're getting right around 1 volt AC RMS on our input. So that is about our desired injected signal level. And the current just has a lot of noise riding on top of it. It's kind of hard to get a meaningful reading, but it's like it says 28 millivolts. So I'll go ahead and write these numbers down. 1, 2, 3, and 28.2 milliamps. And so what's riding on the secondary on the red trace, so the measurement 3, now we're actually using that. That's about 164 millivolts RMS. Again, that's all AC RMS. And you can see that it's following the same contour as the injected signal. So your performance metric in this case, you could just say how much attenuation are you getting? So we're injecting 1 volt RMS on the primary or on the input of the power converter, and we're getting 160 millivolts RMS at the output. So we're getting about 16% of the injected signal. So whatever the reciprocal of that is converted to dB. So it's somewhere around minus 14 or 15 dB or something like that. So anyway, so that's what we have at 30 hertz. Now that we at least kind of have things set up, I think I'm gonna collapse the current scale just a little bit here. Because once we actually start seeing some current, some real current from the injected signal, it'll be a lot more evident. So we're not seeing much current from the injected signal. So that tells me that at 30 hertz, the input impedance is pretty high. All right, so now we'll go to, we'll drop the signal level, maintain good practices. I'm going to drop the signal level by about 6 dB and go to 100 hertz. Okay, we need to drop it a little more. So, because the signal is almost 2 volts. All right. I'll leave it on that scale. All right, so our injected voltage is about a volt. And we might be starting to see a little bit of current coming through. Oop. And it's still riding on top of a lot of noise here. So there's still not much current that's evident from the injected signal. So at 100 hertz, our signal generator setting is minus 25.4 dBm, and we're getting right around 1 volt, 1.005 volts. Our injected current is still about 28, which is pretty much in the noise. And our output voltage is about 142 millivolts. So it's a little more attenuated, so that's good. Or well, it just is what it is, right? But all right, now I'm going to go to a kilohertz. I'm going to drop the amplitude about 6 dB. We'll go up to a kilohertz. Frequency scale. All right, and a little more signal. All right, that's right around a volt. Okay, you're starting to see a little bit of ripple current now. You're starting to see a little bit of the contour of the injected signal on the current. It's still riding mostly on top of high frequency noise, but you're starting to see it. So the input impedance is probably going down. But our output, let me write the numbers down. Minus 31.2 dBm. Our voltage is right around a volt. And the current is still about 28.4. But here again, the number doesn't really tell you much. The number is telling you that it looks about the same as it did, but you can see that there's a little bit of ripple coming through. Now the voltage on the output is the reading is about 68 millivolts. So the ripple on the output is going down. So what it tells me anyway, at least how I interpret that, is the control loop of the power converter is starting to be more effective. Right, the power converter is sampling the input. It's sampling a 28 volt DC level at 400 kilohertz, and it's adjusting, and it's pulse width modulated. It's adjusting the pulse width to give you the desired plus minus 15 volts at the output within the tolerance specified, and you're getting more into the frequency range where that control loop is more effective. So by design, that's exactly how our power converter is working. It's sampling at a much higher frequency than this injected ripple of 1 kilohertz. So without any filtering, right? It's just a bare power converter. The power converter is at least starting to reject the injected ripple at these lower frequencies or mid-range frequencies. So was there a question? I thought I heard somebody chiming in with a question.
Yeah,
Okay.
maybe me, John, just observing along with you the change
Oh.
at 1 kilo.
Okay. All right. So now, now I'll go to 10 kilohertz, drop the amplitude, 6 dB-ish. Go to 10 kilohertz. And then now we're starting to see the switching of the actual switching of the power converter really riding on top of things now. Those big transients there, and in fact, I mean, I already know this from having run through this. At 150 kilohertz, it's going to be much more. Those little ringing, those bits of ringing are going to be a lot more noticeable, right? But anyway, so we'll crank the signal up to get our 1 volt. Much. Okay. I'm going to call that close enough. That's 1.02 volts. So minus 31.2. It's actually about the same as it was at 1 kilohertz. So about 1.02 volts, and the current is about 35 milliamps. But you can definitely see the contour of the current coming into play here. And you can also see a phase relationship between the current and the voltage. So one of the points that I wanted to make here is that when you monitor the current into the EUT along with the voltage, you can get a measurement of the input impedance. And that's exactly, you know, how you do it. You measure the voltage and the current. And when you have enough resolution, you know, on the phase, you can get magnitude and phase. Now, with this noisy input, it's going to be pretty hard. Right, you got all this junk riding on top of the injected signal. That would be kind of difficult, most likely, to get a really effective measurement of input impedance. But a real power converter system that you're going to have on a spacecraft is going to have better filtering and probably will have cleaner signals that you can get a more meaningful measurement of. But this is how you would do an impedance measurement. You would characterize the input and the AC input voltage and the current and the phase between them, and that gives you your impedance, and you do that over frequency. So the output now, you're not really seeing much of the injected signal anymore. You're seeing the switching noise from the converter itself, but the output is it's mostly in the noise, as it were. So it's about 63 millivolts RMS. So so here at 10 kilohertz, the control loop seems to be working really well. Okay. Now let's go up to 100 kilohertz. Drop our signal level again by the 10 dB. Go up to 100 kilohertz. And all right, so our signal level drops, so our input impedance going to go down. The current's gone up, so that's another indication. Oops. There. That's good. Oh, hold on. Actually, I'm going to be increasing the level, right? Because we're only sitting at about 300 millivolts now, so I got to increase the level. Okay, let's all right, the current's gone up noticeably. So our input impedance has gone down. So this is at 100 kilohertz. Signal level is minus 25.5 dBm. So we're sitting right around a volt. AC RMS. It's a very ugly waveform, right? But now let me write the numbers down and then I'll comment. So now our current is up at about 217 milliamps. Current's gone up almost an order of magnitude. Okay, so we're getting into the realm where the input impedance is going down. Right, we're at 100 kilohertz with a switching frequency of 400 kilohertz. That's not real surprising when you get up in that zone of the switching frequency of the power converter. The input impedance is going to go down, and the voltage output is still sitting around 62 millivolts. So we're not seeing a lot of the contour of the injected signal, but we're seeing a lot more of these switching edges. And so if you look up here, we have these noticeable. Again, this is the input voltage to the converter. That's our 28 volt primary. You've got these ringing characteristics here. Well, if we look at the time base, we're at about 10 microseconds per division. And that ringing, well, let's expand the horizontal scale here to make a point. That's 2 microseconds per division. I'm going to stop this because it's a little hard to see with all being all wobbly. But you see that these characteristics are riding on top of our injected signal here, but the ringing characteristics, you know, the period is I'm going to say is from that guy to that guy. That you got these two characteristics. That one is noticeably different from that, but that one looks the same as that. These are the ringing characteristics that we saw on this waveform before we even applied a signal. Our CS101 signal. So from here to here, it's about two microseconds per division. I'm just eyeballing it. That's the period is about 2.5 microseconds. That's our 400 kilohertz fundamental of our switching frequency of our power converter. So
Hey,
that's what you're seeing there. Question?
Yeah, a remark. It looks like current leading voltage by about 90 degrees, so you're well capacitive now.
Yeah. Right. When you look at that phase relationship between the current and the voltage, you'd be able to tell whether the load looks dominantly capacitive or inductive. So yeah, thank you, Ed. The current's, clearly a bit of a distorted waveform. It's not a pure sinusoid, but you can still see the characteristic of the injected signal, and we can see the ringing on the secondary as well. That's lining up pretty much with the ringing on the primary, as you would expect. Right? That ringing is from the switching action of the power converter. But again, at 100 kilohertz, the sampling of the input waveform, the control loop of the power converter is still working pretty well. You're not really seeing a lot of the 100 kilohertz waveform feeding through. So if we finish this up at 150 kilohertz, I'm just going to go to 150 kilohertz because I think the impedance goes up and signal level's going down a little bit. So I'll keep it with that right there. So we need to increase the amplitude just a little bit. Maybe a dB or 2 or 3. There we go. That's good. Okay, so at 150 kilohertz, we're at minus 20.5 dBm. We're right around a volt with injected signal, and our current is now 330 milliamps. And 335 milliamp RMS, and their secondaries hanging around 62 millivolts still. So the input impedance has gone down a bit more. So our current has gone up from about 217 milliamps to about 235. So about about 50% higher, and so on. So that's
Hey, John.
pretty much the extent of the demonstration. So open discussion, questions.
Yeah, John. At this point, what's the peak to peak on the red line?
The peak to peak is well, it's about 0.2 volts per division, so I call that about a half a volt peak to peak.
Yeah, I'm comparing that to the feed through of the 30 hertz, which was 160 millivolts. So it seems like that's smaller than this peak to peak. So
Well,
I guess that's about as good as this converter is in that couple of hundred millivolt peak to peak range.
well, yeah, the we can go back to 30 hertz because I think we were seeing a pretty significant amount of the 30 hertz coming through. Here at 150 kilohertz, we're not seeing much of the 150 kilohertz injected signal coming through. This is just the noise of the converter. And this is
And
what this is pretty much
actually,
what we see above about a kilohertz.
yeah, that's actually more than the feed through of the 30 hertz, which is 160 millivolts.
Yeah, we'll just go back to 30 hertz. And the level was minus 13.8. Okay, so yeah, the 164 millivolt RMS that we're seeing here on the secondary is dominated by the feed through of the 30 hertz injected signal. And I don't, that would be a question for, for the power group. I don't fully understand why the control loop seems to be less effective at 30 hertz, but it seems to really kick in by about a kilohertz. So that
Yeah,
above a kilohertz, we're not really seeing any appreciable amount of the injected signal getting through.
I would think at low frequencies that it would be able to, nod it out.
Yeah. So I said, I don't fully understand that. That's a question. I share the second floor of building 20 with the power group, so I may ask them that question. It also could be, I mean, this is an intentionally noisy and crappy setup. The power converter is just sitting in this plastic box. It's not shielded. It's not, it's not grounded to the table in any way. It's possible that if we did some of those things, a lot of that stuff would get better. But I'm just speculating about that. But the main point here is just the basic mechanics of the CS114 test setup. Oh, as I pointed out, like at the high frequencies, the display on our amplifier was showing like 5 point some volts to get the desired voltage at the output or across the calibration resistor. Well, now it's at 30 hertz, it's showing 2.05 volts. That's right in line with what we would expect, right? Just from
Yeah.
V equals IR. To get
Yep.
well, this is into the UT. This isn't into the calibration resistance. So this may be apples and oranges. But just at the low frequency end, things are a little bit better behaved. At 30 hertz, V equals IR more accurately than it does at 150 kilohertz.
Yeah. Yeah.
I did for anybody who's circulating this stuff for posterity. I better rephrase that. It's V equals IR is a truism, but what I mean is that at higher frequencies, it's more V equals IZ, right? At 30 hertz, your impedance is going to be much closer to the actual resistance. At 150 kilohertz, you're going to have inductance and other things that are going to make that impedance something different from what you think it is. So, but anyway, when you're doing CS101, the pre-calibration step and or the current monitoring is an extremely important part of it. You know, don't forget that. If you're an equipment provider, don't give your test engineers a hard time. Their question?
The same old crap every day.
You got a hot mic, please mute. So, yeah, please don't give your test engineers a hard time for doing the pre-calibration. It's an essential part of the setup of the whole process, the whole procedure, to make sure that you're doing it safely. Now, if you're doing the direct current monitoring method, you can just go straight to that, and that is a recommended approach that a lot of people take. Is you just hook up your current probe if it's part of your control loop, right? If you're just looking at it for information, then you still need to do the pre-calibration step, right? But if you actively connect the measured current, if you actively include that as part of your control loop, and you set, you know, for a 1 volt RMS limit, you set a 4 amp RMS current limit, and that's part of your control loop. And if you hit 4 amps before you get to a volt, you stop. Then that's great, and you don't need to do the pre-calibration step in that case. Pre-calibration, you know, is an extra safety precaution. There's definitely nothing wrong with doing that. It's additional time, but you know, I highly recommend the direct current monitoring method if you've got that capability in your control loop, and that is how we have been doing it at Goddard for a number of years now. So, any other questions or comments? Okay, well, thank you all for participating, and I'll get the recording out later today.
All right. Thank you, John.
Yep. Have a
Hey,
great
thanks,
day.
Sean.
And next week we'll be doing CS114.
Thank you.